We are now moving on to chapter 15.4. From your textbook, it would be page 266. Yeah, it's on impact. Okay, so at the end of this lesson, student will be able to understand, analyze the mechanics of impact, analyze the motion of bodies undergoing collision in both the central and oblique cases of impact. Yeah. So the applications, like the quality of the tennis ball is measured by the height of its bounce. It can be quantified by the coefficient of restitution. I'll come to what is the coefficient of restitution shortly. Yeah? If the height from which the ball is dropped and the height of its resulting bounce are known, how can we determine the coefficient of restitution of the ball? So this chapter will actually answer all these questions. Okay. In a game of billiards, it's important to be able to predict the trajectory and the speed of the ball. So if you are good in this topic, yeah, you definitely will win the game. Yeah, this billiard game. Okay. Yeah. If we know that the velocity of the ball A before the impact, how can we determine the magnitude and direction of velocity ball B? So let's go into the topic. Yeah. Impact occurs when two bodies collide during a very short time period, causing large impulsive forces to be exerted between the bodies. Common examples of impact are the hammer striking a nail or bat striking a ball. The line of impact is the line that passes through the mass centers of the colliding particles. So if you see, if this is the movement of A and this is the movement of B, so the line of impact will be this. Okay, so that is the line of impact. Yeah. Now, central impact occurs when the direction of motion colliding are along the impact line. So you have one going here, one going here. This is central impact. Now, oblique impact comes like happens during billiard ball. Of course, accidents also. Yeah? When the direction of motion of one or both particles are at an angle. Example, something like this. Yeah, this comes in this direction, this comes in this direction, but the line of impact is straight line here. Okay, so these are the two types of collision impact. We have the central impact and the oblique impact. Yeah. Okay, now the central impact, let's just analyze the central impact. Happens when the velocity of the two objects are along the impact line. Yeah, once the particle contact, they may deform if they are non-rigid. Yeah, in any case, energy is transferred between the two particles. These are the two primary equations used to solve the problem. Yeah, so what are the equations? So let's look at the equations. This is the first equation. We have gone through this. Yeah, the conservation of linear equation, and the second equation will be the coefficient of restitution equation. Now, how to use this formula? Now, what is the coefficient of restitution? Yeah, this is a E. It's called by E. Is the ratios of particle relative separation velocity. Yeah. So what actually happens here is that if the E value is 1, okay, if the E value is 1, then you have an elastic impact. So with elastic impact, practically you will see that the particle collide and they bounce back. So very minimal damage, very minimal damage. Yeah, but the E, if it's 0, then it's plastic impact. It means they would have get stuck together and they're moving. Okay, so we have E, which is 0 and 1. So how if the E is in 0.5? So it means 50-50. Yeah, so there would have been some what do you call deformation. How if the value is 0.8? So 0.8 is very close to plastic. So I mean, sorry, very close to elastic impact. So it is like it will bounce back, but there is slight damage. So that is the classification of E between the elastic and the plastic impact. Okay. So how do you calculate this? You put your VB2 minus with VA2. 2 means final. 1 is initial. So the velocities for object B and object A, you plug it in based on the final or initial, and then you can calculate the E. Some questions give you the value of E and tell you to calculate one of the missing component example. So it depends on the question actually. Yeah. Now, next subtopic would be on the energy losses. Yeah. So to find the energy losses, you see, the momentum is conserved, but the energy, of course, it's conserved, but not the kinetic energy. Kinetic energy will lose. Yeah, will lose in. It will change into other forms like noise, heat, or anything else. So that's the reason why you have energy loss. So energy loss here is actually referring to the kinetic energy. That's the reason why we use the T2 minus with T1. Remember what's T? T is half mv square. So if 2 means for case number 2, and for final, and then we have half mv1 square. Okay, initial. Yeah. Okay, so that's about it. Okay, next we'll be moving on to the oblique impact. Now, oblique impact can be a bit more complicated, because reason being, it's actually easy. It's just that you may just create some careless mistake. Look at this. When you have a central impact, it means it is all along which same axis, which is the x-axis. Okay, so whatever that you plug in here, x, 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 you don't have a y here, right? So now the difference in oblique impact, everything is the same, but it's just that now if we solve for x, then it is x. If we solve for y, then it is y. Yeah, so that is the difference. Yeah. Okay, let's look at this. A, x, 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 x. So the eccentric, the coefficient of restitution also x, 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 x. But if you're dealing with y, then you plug in everything with y. You cannot mix up x and y. So it just becomes a bit of extra work. Otherwise, it is actually the same. Okay. So if you see, this is the whole diagram to show the formula, right? Okay. So we have what? Initial, which comes in two direction, because you see this one comes in angle in an angle, right? This angle can be resolved to x and y, so that's the meaning. Okay, and then we have the FDT, and then we have the x and y. So it comes in two different direction, and then you do for object B. So this will be for object B, x and y, and then we have the F in middle, x and y for the final. So it's the same calculation, but it's just that it's being broken up into x and y, and it becomes a bit more tedious, a bit of extra work to calculate, but it is possible. It can be done actually. Yeah, you just have to be careful. So the first thing to do is actually, of course, the initial velocities and particles, or the coefficient are known. Yeah, the final velocities are determined. So it can be anywhere. Yeah, can sometimes be calculating E. Yeah, the questions can be very creative. So this sentence need not to be all the time that it will be the same. Yeah. So the first thing that you should do, define your x, y axis. Yeah, and then you actually draw the diagram. Then you come to, for both central and oblique problem, you actually need to solve based on these two formula. Yeah. Okay. So let's look at an example. I'm going to skip the example on the slide. Yeah, I'm going to go straight to the example of the textbook 15.9. And before I go into 15.9, the angular momentum and moment of forces and principles and angular impulse, that is for your self-study. Yeah. Okay, it's not covered in this syllabus. Okay, 15.9. Let's go into 15.9. Okay, example 15.9. This can be a bit tedious, so you need to pay attention, because it's like a storyline. Yeah, it's like a storyline. Okay, so the back A, having mass of 3, okay, is released from rest. The keyword rest. Yeah. Okay, the position at theta 0, as shown in figure 15.6a. Okay, so theta 0 means this is your reference point. This is the datum. Yeah, datum, where theta is actually 0. Initial datum. Okay, theta is 0. Yeah, after falling to 90 degrees, it strikes a 9 kilogram box. Yeah, so it means this, it will, from A, it will go to this location. Yeah, it will drop 90 degrees, and then it will impact on box B. Okay, so it's like a story, right? So you have to do stage by stage. You have to give them numbers. Yeah. Okay, so if the coefficient of restitution between the bag and the box is 0.5, yeah, determine the velocity of the bag and the box just after the impact. And also they actually want you to also calculate what is the energy loss. Yeah, so I'm going to erase all this, yeah, because it's a bit like messy. Okay, now let's give a numbering. It's a storyline, right? So we have to give numbering. So the textbook has actually called this is the data, and this is case number 0, initial. So can you see 0? And then when it goes down, yeah, goes down, it is number 1. And then when it's down, yeah, it is between 1 and 2. Yeah, they didn't draw. Okay, it's actually between 1 and 2. It means 1, and then this is colliding, this will be 2. Yeah. Okay, let's solve this question one by one. So we have the conservation of energy formula, T naught plus V naught. What is T? Your kinetic. Your V will be all the forces, but in this case it is only mgh. Yeah. So since the datum is high up there, mgh is actually 0. So we have half mv square minus with mgh. So what's the height? The height that it travels? 1 meter. Because you see from here, it actually drops 1 meter, vertical height 1 meter. Yeah, so that's the reason why it's being multiplied by 1. Okay, so we have 4.429 velocity of A initially. Okay, so now we can apply the conservation of momentum formula inside here. Okay, so with the momentum formula, what do we have here? VB initially is actually 0. Yeah, the box was actually stationary, right? Yeah, now the story is between 1 and 2. Okay, now remember 0 and 1 is up here. Okay, 1 and 2 is between the box coming down and the the sack coming down and the box number 2. Okay, so we have 1 and 2. So at point 1, this box was stationary, so that's why it is 0. Yeah, at point 1, the velocity was actually 4.429. You just calculated that, right? Okay, and then we have MB, VB. So M of the box is 9 and the V of the box, so it's now moving. Case number 2, the box is actually moving, but we do not know what is the velocity. So leave that alone. So we have 3 times with VA2. Yeah, of course, after the collision, the sack, we don't know what is the velocity of the sack. So you have one unknown here. Yeah, so you have one equation here. You call that equation 1. Okay, so now with the coefficient of restitution, yeah, coefficient of restitution is given as 0.5, right? Okay, with that hint, now looking at this formula, can you fill up all the values that you know? Yes, isn't it? Because this is 0.5, you know what's VA1, you know what's VA2, but up here you do not know these two values. So what happens here, when you plug in, you are actually getting the second equation. So with equation 1 and 2, you can actually solve simultaneously. You can find the unknown. So these are the unknowns. Yeah, so we have VA2, which is in that direction, VAB, which is in the opposite direction. So if you get a negative value for VAB, it means the direction is in the opposite side. Okay, so what is the actual, that is just to calculate that. Now what is the loss of energy during the collision? So we have to use your half mv square. Half mv square final minus with all the energy that is initial. So what we have here is that, so when you add the when you add all the total final and you minus with the initial, so you get negative 16.6. So that is the energy loss due to the inelastic deformation. Yeah, so when the E is actually 0.5, it means that is about 50% of plastic deformation and 50% of elastic. Yeah, because the value of the question for E is actually 0.5. Okay, so with that, I've actually ended chapter 15, successfully ended chapter 15. So please do all the questions that is actually given on the e-learn, yeah, and submit them on time. Thank you.